While the night sky appears limitless, physics dictates a precise spherical boundary for our observations. Every photon reaching Earth originates from within a specific, finite volume of space. This is the observable universe. From our position at the center, the distance to the edge is exactly 46.5 billion light-years in every direction. This limit exists because space is expanding. Distant regions are moving away from us so rapidly, but the light they emit will never close the gap, no matter how much time passes. Every piece of data we can ever collect is confined to this volume. Our perception of the cosmos ends where the expansion of space exceeds the speed of light, keeping us isolated within this local bubble. Within this environment, cosmologists track two distinct boundaries. The particle horizon defines the furthest light that has reached us since the beginning of time. The event horizon, however, represents the limit of any future interaction. Dark energy accelerates the expansion of space. As the grid stretches, distant galaxy clusters are pushed past the event horizon. If we send a light signal toward these receding galaxies today, the expanding space prevents it from arriving. Our causal connection is permanently severed. These expanding horizons represent the hard physical boundaries of our observable world. They force us to rely on theoretical models to describe the forces operating in the vast portions of the universe we can no longer see. We can see structural anomalies much closer to home as well. Within our own observable bubble, astronomers have identified massive regions that are almost entirely empty. In a typical 330 million light-year volume, we should find about 10,000 galaxies, but in the Boody's void, we've detected only 60. These voids form as dark matter pulls ordinary matter into dense filaments. While gravity builds this webbing, dark energy inflates the empty spaces left behind. Spatial nothingness is an active structural component of the universe. These voids are physical architectures carved out over billions of years by invisible cosmological forces. Looking across these vast distances of space is also a way of looking back through time. At 13.8 billion light-years away, we hit the temporal edge of our history. In 1964, this instrument, the Holmdel-Horn antenna, detected the literal edge of the visible past. It picked up a persistent microwave static known as the cosmic microwave background, the first light to travel freely through the universe. We cannot see anything before this point because the early universe was a superheated, opaque plasma. Photons were constantly blocked by free electrons, trapped in a chaotic environment where light was unable to propagate. This plasma wall acts as a permanent barrier to our telescopes. To probe the Big Bang singularity itself, physics must look past the light and rely entirely on the mechanics of math and theory. This creates a question of origins. If the Big Bang was the beginning of time and space, what could have possibly existed before it? Philosophy often describes absolute nothingness as a total absence of being, but physics provides a different definition for empty space. Even in a perfect vacuum, space is never truly empty. Virtual particles are constantly popping into existence and annihilating. Some models suggest our universe didn't emerge from non-existence, but rebounded from a collapsing previous universe in a big bounce. If these models are correct, the pre-Big Bang state was not an absolute void. It was a highly energetic, unstable foundation that provided the raw materials for our reality. Tracing the universe's trajectory into the deep future reveals a transition from these energetic origins to a period of permanent isolation. As dark energy continues to accelerate the expansion of space, our horizons will merge and appear to collapse inward. Distant galaxies will slip past this boundary, disappearing from our view forever as the space between us expands faster than light. Future inhabitants of our galaxy will be physically cut off from the rest of the cosmos. They will live in a universe that appears empty, with no visible evidence of other galaxies or the Big Bang itself. After trillions of years, the universe enters the degenerate era. Stars will cease to form, leaving only black holes and the cold, dense remnants of dead suns. Even these black holes have a finite lifespan. As Stephen Hawking theorized, they will slowly leak mass through a quantum process called Hawking radiation, eventually evaporating into the void. The final state of the cosmos is heat death. Protons may decay, matter will dissolve, and all remaining energy will spread so thinly that the universe reaches a permanent frozen equilibrium. This dynamic, structured universe is a temporary state. Its ultimate destiny is a return to a condition that resembles the absolute emptiness of the beginning. The Anthropocene, the current era of human civilization, occupies a very specific point on this vast timeline. We exist in a rare window of cosmic history, late enough for stars to have forged the elements of life, but early enough that the expansion of space hasn't yet hidden the origins of the universe from our sight. Our ability to observe these edges of reality defines this era. We are witnessing the universe at its most visible, just before the final horizons inevitably close.